right, so today we're going to look at something called an alternating series and to determine the convergence or divergence. And this one is actually very obvious when this one is used. It's actually, after p-series and geometric, we tend to use alternating. But usually there's a negative in there somewhere and it tells you, you know, where things are, that is obvious, very obvious. All right, we ready? Okay, I'm going to give you a minute to fill in all the blanks. All right, so for an alternating series, it should be obvious. Alternating means the signs are going to go back and forth, right? So we're going to have a minus plus, minus plus, minus plus situation going on with your terms, okay? You tend to see a negative 1 to the n or something of that nature in the series, and that is a really good red flag that that's an alternating series, okay? So it has to meet two conditions, all right? The limit as the series approaches infinity has to be 0. If it doesn't meet that, then it, I believe it diverges, actually. Yeah, it says it diverges. And then the terms have to be decreasing. So as long as the terms are decreasing, then it will converge. So there's two ways we look at the terms decreasing. I'm going to show you both. One of them is we can do the first derivative test to look at decreasing. And then the other one is we can actually just list out the terms, but you sometimes have to be careful to make sure you list out enough of the terms, okay, to see if it actually is trending towards decreasing or not, okay? All right, so we're going to determine the convergence or divergence. So the first thing I need to look at is, does it look alternating? Yeah, so we've got that negative 1 to the n, so we would use the alternating series test. So the really step one is we need to look at the limit as n approaches infinity of 1 over n. And we have to double check to make sure it equals 0. So when I put a 0 in there, what happens? Or sorry, an infinity in there, what happens? It does equal 0. So we verified that. You basically have to make that statement. So then what we need to look at is what's going on with the terms of this thing. So let's start making a list. If I put in a 1, what would I get? 1. Okay, if I put in, and technically it's probably going to be a negative 1. Am I worried about the signs here? No. So alternating, we're not super worried about the signs. We're looking at the terms decreasing because we know the signs are going to alternate back and forth. All right, what's my next term? 1/2. What would my next one be? 1/3. All right. So do you see, are the terms going down? Yeah, they're getting smaller and smaller and smaller and smaller. All right. So the way I happened to state it on this one was that when we know we've got 1 over n is the series. When we add one more to the n, right, we put another one in, we know that it is smaller than the original. Okay. For all n greater than or equal to 1. That's basically the statement that says we know that it's decreasing, okay? So that proves the decreasing because we were able to make that statement. So then we would say, therefore, our series from n equals 1 to infinity, negative 1 to the n, 1 over n converges. I don't know why I put parentheses around my 1 over n. It has to, the limit has to be 0 and it has to decrease, it converges. Okay? As long as it's alternating. All right, we good? Almost. Sorry, too fast. All right, we good? Okay. So, example 2, we've got, is it alternating? Yeah, we've got the indicator that it's alternating. So let's go with, we got to look at our limit as n approaches infinity of the natural log of n over n. All right. Can I just plug infinity into that? No, what do we need? We need good old L'Hopital's rule. So when I take the derivative of the natural log of n, what do I end up with? 1 over n. What's the derivative of the n? 1. Is that okay? Oh, I lost my limit, didn't I? Limit as n approaches infinity. If I wrote it cleaner, you don't have to, but we really are down to that. What's that limit? 0. So do we verify that it equals 0? Yep, so condition 1 is met. All right, this one, I'm going to go ahead and use the first derivative test. So we practice that. I think we're going to practice it 2 times. Okay. This one, it's harder. The reason I'm doing that is it's harder to tell when we put in that natural log of 1, especially without a calculator, right? What is the natural log of 1? What is the natural log of 2, 3, and so on. So that's why I'm using the first derivative test here. So my original function, I'm just going to switch it to x's even though I know it's n, is that. What rule are we going to have to use? It's been a long time. Quotient rule. So low d high. What's your low? X. Derivative high. 1 over x minus the high, which is natural log of x all over the low squared. All right. What cancels to begin with? X's. So we got 1 minus the natural log of x over x squared. So what do I have to do now when I'm talking about derivatives and my first derivative test? What do we typically do after this?
I have a Nostrum Group Award for Maria Delgado. Award for Jess Leah. And you guys have 2. Woo!
All right.
Thank you.
You're welcome. All right, so the next one we do is set equal to 0, get critical points, right? Okay, so critical points. So we'd have 1 minus the natural log of x equals 0. So 1 equals the natural log of x. How do I get rid of the natural log? Exponentiate it. So we know that x is equal to e. Where's our other critical point from? 0, right? The denominator. So, but if I look at the interval I'm working on, because isn't this the interval 1 to infinity? So really we're looking at, it says that we have a critical point at 0, we have a critical point at e. I'm really needing to look at what's going on up here, okay? So what number is bigger than e?
3.
3 would work, because e is 2.718. Could I put in 10? Yeah, okay, and remember I go into my derivative right there. So is the denominator going to have any bearing on this? No. Okay, so put a 3 in, do 1 minus natural log of 3 on your calculator and tell me if you get a positive or a negative. Negative. So is it increasing or decreasing? It's decreasing. So it passed, we know by the first derivative test that this is a decreasing function. So you can use a therefore symbol, another symbol that we can use. This is called implies. Okay, the little funky arrow. So this implies that the natural log of n over n is decreasing. Okay. Then I'm going to use my little therefore. I'm going to put it up at the top though. Okay. Therefore, we know the sum as n equals 1 to infinity of negative 1 to the n natural log of n over n converges. So I used the implies so I didn't have to do therefore twice in a row, right? Change your transition word. All right, we good with 2? Yeah? All right, let's take a look at 3. Okay. So, we're going to start, first of all, does it look alternating the way it is? It doesn't look alternating the way it is. What happened? Oh. It says the cosine of pi n, right? Okay, so let's think about what that really means. Okay? When I put in a 1, right? When I put a 1 in for the n, I get the cosine of pi. What's the cosine of pi? Negative 1. When I put in a 2, what's the cosine of 2 pi? 1. So is it alternating?
Yes.
Yes, it is alternating. Okay. So it's really equivalent to the statement. We could get rid of that, couldn't we? Because we know it's just going to alternate. So it's really negative 1 to the n times 1 over n to the 3/4. Because all this is going to do here is alternate the negative 1 back and forth, isn't it? So we're going to rewrite it to that series. All right, so we know it's alternating. The next thing I need to check is the limit. So I'm going to do the limit as n approaches infinity of 1 over n to the 3/4 power. Okay, so when I put an infinity in here, what do we end up with? 0. So did that work? Yes. Okay. We've got 1. Then we've got to check our terms, right? So I'm going to make a list of my terms and see what happens, and we'll make the statement if that works. So I'm starting by putting in a 1. When I put in 1 to the 3/4, what do we end up with? 1, right? And then we're going to put in 1 over 2 to the 3/4, then 1 over 3 to the 3/4, and 1 over 4 to the 3/4. So what's happening with this number on the bottom? Is it getting bigger or smaller? It actually ends up getting bigger, right? Because even though we're only raising it to the 3/4 power, it's still making the number bigger really fast. So is it decreasing? Yes. So we want to make the statement. Okay, we put the number on the bottom's getting bigger, which means overall the number's getting smaller, right? Okay. So we got 1 over n to the 3/4. Remember the way we phrased the statement was we did an n plus 1 over there. And we've proven that this number here, that when we add 1, is smaller than the original for all n greater than or equal to 1. Okay? So therefore, what happens? It converges. And we're going to go back to writing the original series down, not the one we adjusted it to. Okay? All right, we good with example 3? Okay. Looking at example 4. We okay? All right, we've got up to 7 today. Wow. All right, so is it alternating? Yes. Okay, oh, this one's short. All right, so we're going to look at our limit. Limit as n approaches infinity of... Can I ignore this thing up front here? Yeah, I can ignore that. I basically use what's in back. N over 1, or n plus 1 over n. All right, so what do we know about this limit? It's 1. So is it equal to 0? No. What happens with this series then? Diverges. I told you it was short. Therefore diverges. If you want a reason, at least for your notes, it's because condition number 1 is not met. All right, we good with 4? All right, is number 5 alternating? Yeah, we've got the indicator for alternating. Okay, so let's try our limit on this one. Limit as n approaches infinity of 2 to the n cubed over n cubed plus 4n minus 1. What's that limit? 2, so what happens? Diverges. I'm not going to write the reason on that one because it's the same as the last one. We like it when it's like that, right? It's way easier. All right, let's look at 6. So, is it alternating? Yeah. I'm going to ignore that -1 part for my limit then. So the limit as n approaches infinity of 1 over the square root of n plus 3. Okay. So when I put an infinity in, what do we end up with? 0. Okay. So I'm going to use, because this one isn't super great, we're going to practice our first derivative test again. Okay. So first derivative test is what I'm going to use. So my original is f of x equals 1 over x plus 3 to the 1/2 power, which is really x plus 3 to the -1/2 power. All right, so f prime of x equals, what are we going to do with this? Bring it to the front. So -1/2 x plus 3 to the what? -3/2. So if I cleaned it up a little bit, I'd end up with this. What's always going to happen here? It's always going to be negative. So what does that mean about the function? It's always decreasing, right? So this implies that it's decreasing. I don't really even need to do the sign chart part, right? Because we know it's decreasing because of the negative there. So therefore, what happens? Therefore, sum is n equals 1 to infinity of -1 to the n. It's -1, not +1, right? Over the square root of n plus 3 converges. That's a C. Converges. For some reason, everybody seems to like this one. So this is usually one of the favorites.
Is it your favorite?
No. But it's not that difficult. I'm still holding my record. I haven't had to look back at the videos this year. I'm doing good. Just looking back at my notes. I don't even have to look at them that long. All right, look at this one. This one's a little bit goofy. Is it alternating? It looks... Oh, actually, you know what? There's a typo. That shouldn't be there. Now, is it alternating?
No.
Look at the denominator.
Dang it.
Is it alternating? It's just a 2 instead of a 1, right? So it is still alternating, okay? I could probably rewrite that and make it look more alternating, just like the cosine one. That's really the same as -1 to the n minus 1. And I have to use the same exponent on the 2 to the n minus 1. So this thing here, even though it's in the denominator, it's still going to alternate the sign for us. So we've got the limit as n approaches infinity of, and I'm only going to use what's in the back here, n over 2 to the n minus 1. All right, that would be indeterminate, right? I get infinity over infinity, so what do we need to use? L'Hopital's rule. So we've got the limit as n approaches infinity of what? 1 over... Good. Natural log of 2 times 2 to... Remember, that's a derivative we haven't used in a while. All right, the upside is it doesn't matter. When I plug an infinity into there, what do we end up with? It's going to be 0. So that part checked out. So now we have to prove decreasing. I'm going to go by the terms this time. Okay. So we really need to look at plugging the terms into this thing right here, right? Because we know the signs are going to alternate. So I'm going to start by plugging in a 1. So we get 1 over what? 1 over 1. Because it's 1 minus 1 is 0. 2 to the 0 is 1. Okay. All right, let's plug in a 2. So we get 2 over 2, which is really just, has it decreased yet? No, it stayed the same. All right, let's keep trying. Put in a 3, we get 3 over what? 3 over 4. Okay. And then it looks like it's decreasing, but we better go a little further just in case, because this one was weird to start with. All right, so we're going to go 4 over, let's see. It would be 2 to the third, which is, now are we fairly confident that it's decreasing? Yeah, so we're implies that it's decreasing. Okay. Jacob wants to go further.
No.
Just to make sure. If it was my AP test, I might go further, just to make sure. All right, and we can say that it converges. Okay, so not too bad. It's not like we're having to do the integral test. All right, that's probably one of the worst ones. All right, assignment for today. I'm waiting.
Stay strong, kiddo.